So let's take a look at a simple example. Let's take a look at a simplified model of a protein that's in the Drosophila embryo called Bicoid. So we've talked about morphogens just a little bit, but basically a morphogen is it's a protein, or it could be a small molecule, but it's made in a particular place in the embryo. It spreads through diffusion. The cells read that concentration and capture it, and then they respond in a differential fashion depending on how much concentration they're reading. These morphogen gradients, they're established by localized secretion. So there was this Q of X term that I had, where Q of X was equal to some value over the blue cell and 0 everywhere else, right? So over the red cells and over the yellow cells, although I don't have yellow, so I'm going to color it orange. You have the green cells, right? So I just mimicked this tissue drawing here. So that's Q of X, right? So it's equal to, say, some value Q0, which is the rate of secretion of the protein by the blue cell, over the blue cell, and everywhere else it's 0. Right, so localized secretion, Q of X. Now, in the lecture on receptors that I posted about this Q of X, you could make it look like this, or if this domain over which the morphogen is secreted is very narrow, sometimes you can treat this as a boundary condition. So this could be or constant flux boundary condition. That's sometimes how we treat that. And that's how we'll do it in this example problem here. Morphogens also typically, when you write down equations, they typically have some sort of global degradation term, right? Some first order degradation, because you don't ever assume that a protein has like an infinite lifetime. And then you have diffusion, which of course is d times your second derivative in space. So people had thought that these things called morphogens were around. They'd kind of hypothesize about them. Actually, they've been hypothesized since sometime in the late 60s by a very famous developmental biologist named Louis Wolpert. And he said, if there's a protein that is produced at one end of a tissue and degraded elsewhere, although his degradation he thought was at the other end, but typically it's degraded everywhere in the embryo, right? So localized secretion, global degradation. And he said that would develop a concentration gradient in space of this protein, and the cells, if they respond in a concentration-dependent fashion, let's call that a morphogen. Now, morphogen is a word that I think comes from the Greek, and morpho means form, and gen is like generation or forming. So it's forming. It's a protein that is responsible for forming the form of the tissue, for causing different domains of gene expression to happen. So even though this idea of a morphogen was first hypothesized somewhere in the late 60s, it took about 20 more years for any molecule known to be experimentally confirmed to act as a morphogen. And so this first one that was confirmed to be a morphogen was a protein called Bicoid in the fly embryo. So Bicoid, as you can see here, this is an image of a fly embryo. This is about a half a millimeter long, 500 microns long here. This part here on the left-hand side is what's known as the anterior pole. At the other end is the posterior pole. And what you can see is that the Bicoid mRNA is localized to the anterior pole. Now, Bicoid does have a concentration gradient. At least the protein. Protein has a concentration gradient. So it might be kind of dark for you to see, but there is more red fluorescence at the anterior pole And in a continuous fashion, as you go towards the posterior pole, it becomes darker or less and less intense. And actually, if you were to quantify this, with the exception of some funny business, here, let's draw in some little numbers here, 0 and L, where L is the other end of the embryo, except for some funny business happening at the anterior pole, Bicoid protein is almost perfectly exponential, exp to the minus x over lambda. And also, cells respond to Bicoid, which is abbreviated BCD, Bicoid concentration respond to Bicoid in a concentration dependent fashion. So cells that are perceiving the highest amount of Bicoid in their region, they are going to turn on certain genes. And cells that are further away are going to be able to read a lower Bicoid concentration, and they'll turn on other genes, et cetera, on down the line. And unfortunately, these graphs got split up onto different pages. So first you have this multicolored embryo on the bottom of page 4, and it's not until you scroll down to the top of page 5 that you see the kind of the quantification of that image. But essentially what we have is we have a protein called hunchback, or HB, that's in blue. We have a protein called giant, abbreviated GT, that's in green. We have one called crouple, and you know what? Again, I don't have yellow, or I don't want to use yellow because yellow doesn't show up that well. They have one in yellow, which I'm drawing here in orange, is crouple. I know these names are weird. And then you have one in red, which is one called Knerps, or KNI. So the colors that I wrote here correspond to both the graph and the embryo on the previous page. So the cells, they respond to Bicoid in a concentration-dependent fashion. And we know this because we can have embryos that are loaded with higher concentrations of Bicoid protein, and these cells will change which genes they're expressing. So if we load the embryo with more Bicoid, then, for example, this boundary here of hunchback, let me scroll down so we're just looking at the graph now, pretty much. This boundary here of hunchback, which I don't know what is the best color to draw in because I don't want to pick a color that overlaps with all the colors you see. This boundary here of hunchback, where it suddenly drops from high to low, the blue is high, and then suddenly it drops to low, and we can say, well, where is the location at which it's like 50% of its maximum? Right, so if this is 50%. And that location is about, let's call that X hunchback. That location is approximately equal to 0.5. And that's in a normal embryo. It might be more like 4.7 or something, I don't know. But just for our purposes, let's just say it's 0.5. Okay, so this boundary, and these cell boundaries, these gene expression domain boundaries, they're very well defined because you have high, then low. You have on, off, pretty much. There's a little region in between where you have some intermediate values, right? But it's mostly on, off. So these boundaries are pretty well defined. If I load an embryo with twice as much Bicoid as normal, this X hunchback moves to a higher value. It moves posteriorly. And then other genes shift around as well. So we know that Bicoid is concentration dependent. It has a concentration profile, and the cells respond in a concentration dependent fashion. Okay. All right, so what kinds of models can we write down for this? So it has a localized source. It has diffusive spreading. And quite honestly, we're not sure about whether it's degraded or not, but you almost never assume that a protein has an infinite lifetime. So we're going to assume global degradation. Like it has to get degraded over time. Otherwise, it's just going to accumulate in embryo forever. So the model for this would be dc dt, partials, I should say, equals to a diffusivity times this diffusion term, the second derivative in space, minus global degradation. That's a k times a c, where c is the concentration of Bicoid, plus this q of x term, this localized source. All right, so you have localized source is q of x, you have global degradation is this kc, and you have this diffusive spreading, which is the first term. Right? So q of x, as I said before, is equal to something high in a certain region between, like, say, 0 and x naught, and then 0 everywhere else. Let's say it starts at q naught and then goes down to 0. Okay, but if x naught, if this domain over which Bicoid is locally produced, because that's where the mRNA is, if that's narrow enough, we can go ahead and just like simplify things, and we're going to shove q of x into a boundary condition. And when we do that, we're going to get something that looks more like this. Let's not draw arrows. Let's just draw a little box for the embryo. So here's our box for our embryo. We have the anterior pole at x equals 0, posterior pole at x equals L, and we have constant flux. So just this anterior boundary is sort of just producing Bicoid, right? So constant flux. At x equals 0. And that would be the negative d dc dx evaluated at 0 equals some constant term q, capital Q. All right, so we've got about 10 minutes left, and I think we're not going to get to the end of the Bicoid example. So I'm going to go through this. It's going to carry over to the next lecture. Next lecture, we're going to talk a little bit more about a couple other examples in development, and then that'll be the end of Module 2. Okay, so let's go ahead and get through this. Before I do that, since I know this is going to spill over, why not just waste a little bit more time? And you might be wondering, like, what is this Q? Why is it a Q, right? I keep saying Q of x here, and I said the constant flux is equal to some constant, say Q. Heat in thermodynamics, Q, right? Other times like this, you have some Q, which is some source of something, right? So Q in German, the word for source in German starts with the letter Q. So that's where Q comes from all over the place, right? So our source of Bicoid is Q. Heat is a heat term in a thermodynamic equation. That's the source of heat. That's the Q, right? Interestingly enough, there is a biblical connection to that. So if you think about like the Gospels, Luke and Matthew probably base a lot of their gospel on the Gospel of Mark. In addition to that, there is some material that they have in their Gospels that aren't in Mark. Where did they get that material? Well, German scholars thought that there was just some source out there that they read that they got their material from. What is that source? They don't know. They don't know who it was. It's not a manuscript that anyone's ever found. So they call it Q because it's the source. So that's just, it's in chemical engineering. It's also in biblical studies. Okay, so back to the lecture. We have a constant flux, and we're going to assume that we're at steady state. So if we're at steady state, then you have a 0 accumulation term. You have your diffusion term. You have global degradation. And you have the source term, but we put the source into the boundary condition, so it's not actually in the bulk equation. So this bulk equation is subject to a constant flux boundary condition, And at the other end of the embryo, Bicoid can't get out, so that's a no-flux boundary condition. So if a Bicoid molecule happens to make it to the other end of the embryo, it's going to bounce off and come back. That's no flux. Oh, I already said that. That's interesting. Okay, yeah, so it's no flux. What should the boundary condition at L be? No flux. All right. Bicoid can't escape from the posterior end of the embryo. There's also no reaction happening there, and no reaction happening. Right, so it can't get out. It's not like being degraded just at the posterior pole, so there's no reaction in the boundary condition either. So it's just no flux. So if you guys are in fluids or heat or mass, some transport class, you probably run into the Buckingham pi theorem, which is like, how many different parameters can we group together and non-dimensionalize our equation, right? We're not going to apply that, but you have the idea of non-dimensionalizing your equation in your mind. And so what we're going to do is we're going to go ahead and non-dimensionalize our equations. So we're going to say let x hat be defined as x over L, and c hat. By the way, I don't know if I could explain the Buckingham pi theorem to you. I just know that it exists. And I saw it in class like some 30 years ago. 30 years? No, I'm not that old. 25 years ago? No, I'm not that old either. 27 years ago? Anyway, something like that. Okay. And c hat is defined as c over c bar. Okay. So we're going to non-dimensionalize our equations. We know what L is. What is C bar? I don't know. We're going to find out. So we'll just stick with it. We'll just pretend like there's some sort of C bar, and we'll find out what that is naturally later. And this is what you might typically do, right? There's some concentration scale embedded within the equation somewhere. And we're going to find out what that concentration scale is when we work with the equations and it falls out. Okay, so we'll get there. Okay, all right. So let's go ahead and non-dimensionalize these equations. So that these transformations give us the following: you have 0 is equal to our diffusion term, which is d times dc dt, but c is c hat times c bar. And I said dc dt, I meant dc dx. And it's not x, it's x hat times L bar, or just L. And that's squared. Right, it's a second derivative. So x is squared, which means L is squared. So all I've done here is I've taken d squared c dx squared, and I pulled out the c bar, and I pulled out the L squared. Okay? And then you have a minus k times c. But again, c is c bar times c hat. Okay, so perfect. And now that we have this equation, we see that since it's at steady state and it's 0 on the left-hand side, the c bars cancel. So we can rewrite this equation as 0 is equal to, I'm going to take the d and the L squared, I'm going to move it over into the second term. Okay, so 0 is equal to d squared c dx squared, hat, minus this grouping of constants, which is k, L squared over d, times c hat. Okay, question. Does anyone know what this grouping is? There's a name for it in chemical engineering circles, k L squared over d. Has anyone seen that before? The what? Not quite. It starts with a T, TH. It's the Thiele modulus. That's what it's called. So this is the Thiele modulus. And if you've had heterogeneous reaction engineering, you'll have seen it. This is phi squared. The Thiele modulus is phi, and this is the square of that. So that's one way to write the equation, is by grouping all of these constants into the second term, and then you have this Thiele modulus. Now, whoever came up with this, probably a guy named Thiele, whoever came up with this, I don't like what they did here. It doesn't seem natural to me to have the Thiele modulus there, to have the grouping be on the degradation term. Me personally, I would have loved for it to have been rewritten in a different way. I would have loved for it to be rewritten this way, where you have d over k L squared times your diffusion term. And by the way, I'm going to drop, where can I write this? Drop hats for simplicity. I'm just going to get really tired of writing all these hats all the time. So we're just going to drop them. Okay. So I would have loved for him to have written it that way. And in that case, then, this grouping, dk over L squared, this is your dynamic length scale lambda squared. That's what that grouping would be. Such that lambda is equal to your dynamic length scale in dimensional units normalized by L. So that, to me, that makes more sense, because it is a length scale. This d over k, the square root of d over k, it's a length scale. It tells you how far into the embryo you're moving. So if Bicoid moves far, then lambda's big. And if Bicoid doesn't move very far, then lambda's small. So I don't know. I just prefer it that way. But as chemical engineers, we should be good, and we should write this as a Thiele modulus. Okay, let me finish. I know I'm about to run over time, but let me finish this last thing by, and I think I haven't given myself enough room, so I'm going to make a little gray box here, because I didn't write the boundary conditions yet. I did, but I haven't non-dimensionalized them. So we are subject to boundary conditions, and the boundary condition for the no flux is easy. It's just dc dx evaluated at L, but it's not L anymore, it's 1, because we normalized out L. That's equal to 0. So that's our no flux boundary condition at one side. And at the other side, we have our constant flux boundary condition, which is negative d. If I pull out the c bar, I have c bar. If I pull out the L, I have L in the denominator. dc hat dx hat, but again, without the hats, evaluated at x equals 0 equals q. So that's our no flux, that's our constant flux boundary condition, non-dimensionalized. And let's go ahead and group all these constants together as well, or we have dc dx evaluated at 0 equals to negative L q over d times c bar. So remember earlier what I was saying is, let's go ahead and just say there's a c bar. There's some concentration scale embedded somewhere in the equations, and we'll just work with it and find out what that concentration scale is later. Here is our concentration scale. This is the only place in the equation where there's some parameter that's going to tell us how big our concentration is. That parameter is q, and so therefore our c bar is equal to L q over d. And so if we adopt the c bar being L q over d, then our constant flux is equal to negative 1 on the right-hand side. Right, this becomes negative 1. All right, so we have this equation, we have these boundary conditions. How are we going to solve them? And the answer is, you just know. You just know the answer, and the answer is it's exponentials. Now, you get used to that as you do this kind of stuff over and over again. But if you're not used to it yet, you're kind of like, this seems like a cop-out, right? We're supposed to be able to, like, I don't know, reason things out logically or rationally, rather than just being told the answer. And I don't know how to help you overcome those feelings of doubt, except to say, there are some things we do know about these differential equations. And one of them is that these solutions, they're unique. Or they're unique up to, a multiplicative constant, right? They're unique. And so if the exponential works, then you know you have your answer. There's no other answers that you have to worry about. It's not like, hey, I guessed exponentials and it worked, but maybe there's something else out there. And the answer is no, there's not. Since it's a second order differential equation, you have a linear combination of two different exponentials that both work. Okay, so that's it. All right, so I'm going to do it the dumb way first. Okay, I'm going to say that our concentration as a function of x, and I'm going to call this C1 because we're going to try two different exponentials. Since there's a second order derivative, you have two different potential solutions. So the first one I'm going to try is C1 of x equals to A1 times E, or exp, of this Thiele modulus x. Okay, so I'm working with a Thiele modulus version of the equation. Doesn't matter, either way. Okay, so that's a guess, and we're going to try it. Try it. It's not really a guess. I know it's the right answer, but here we go. The reason why you know it's the right answer is because you tried it. Okay, so let's plug it in. So 0 equals d squared c1 dx squared minus Thiele squared c1. So if I plug in c1 into there, what you get is 0 equals, the second derivative of c1 is just a1 Thiele squared e to the Thiele x. Minus, now that we just plug in c1, a1 Thiele squared. I guess technically it's Thiele squared first, right? So Thiele squared times c1, which is a1 e to the Thiele x. Okay, so you see that this works, right? It was a good guess. Right, so those two terms cancel out, and they equal to 0. So c1 equal to some constant a1, which we don't know yet, e to the Thiele x, that works. That's just the right answer. That's a right answer. And there's only one other right answer, because we know that there are two unique answers. Or technically there's a family of two sets of unique answers, but we'll get to that in just a little bit. Okay, so that's one. It worked. Let's try another one. C2 of x equals a2 e to the minus Thiele x. So we're going to try it as well. So again, we're going to plug in, and it works. I don't know if I want to go through this. Let me just say try it, but I can just say it works. Just trust me, or you can do it on your own. If you do plug it in, it works, right? So it's good. We have two different solutions. They both work. They're independent of each other, which means it's not like one is a constant multiple of the other. So they're linearly independent solutions, which means that the real solution is some linear combination of the two. So C of x, the full solution, C of x, is equal to a linear combination of the two. Since they already started out with arbitrary constants, and linear combinations multiply arbitrary constants onto these functions, I don't need to redefine these arbitrary constants, right? So the full solution is a1 e to the Thiele x plus a2 e to the minus Thiele x. And that's my full solution. It's a family of solutions because I don't know what a1 and a2 are. Okay, so how do you find a1 and a2? I mean, this is a real physical system that we're modeling, so there should be a real physical distribution of concentration of Bicoid. So that means that there needs to be a real physical A1 and A2. So what are they in this particular case? How do we find them? We need the boundary conditions, right? So we're going to use our boundary conditions to define or to calculate A1 and A2. Okay, so that's it. So plug into boundary conditions and find A1 and A2. However, remember, we have families of linear combinations of these two solutions. And how do I say this? We could find a different way of representing this family of linear combinations of solutions. In particular, this family of linear combinations of solutions could also be represented by hyperbolic cosine and hyperbolic sine. As annoying as that might sound to some people, these are just different functions. They're not e to the x. They're just something else. It's just a different function. We know what they are very well. For example, hyperbolic cosine looks like this, and hyperbolic sine, I guess I should say technically hyperbolic sine of x and hyperbolic cosine of x, they're drawn there. And so they have very specific ways that they look, and they're just two different functions. They're different from what you normally are used to, but they're legitimate. And they're defined in the following way. If you haven't seen these, or if you need a refresher, hyperbolic cosine of x is equal to 1/2 e to the x plus e to the minus x. Hyperbolic sine of x equals 1/2 e to the x minus e to the minus x. So each of these are just linear combinations of the two exponentials we already said were solutions to the equation. Because of that, linear combinations of hyperbolic sine and hyperbolic cosine are also equally valid solutions to this differential equation. So that's what we're actually going to work with. Okay? We're going to work with hyperbolic sine and cosine, not exponentials. Now, one of these boundary conditions is a no-flux condition, right? So we have a no-flux boundary condition at x equals L. So dc dx at x equals 1, because it's scaled, that's equal to 0. So we're going to take advantage of the fact that hyperbolic cosine already has a derivative of 0. So hyperbolic cosine already automatically solves or satisfies one of our boundary conditions, except it satisfies a boundary condition at x equals 0, but the boundary condition where we have no flux is at x equals 1. So how do we do that? We're just going to do a coordinate transformation. Okay? So what that means is if we let C1 equals to A1 hyperbolic cosine of phi times 1 minus x, then we automatically satisfy no flux at x equals 1. That also means that A2, which is the pre-multiplier for the, well, let's say it this way. If we take hyperbolic cosine as one of them, then C2 has to be equal to A2 hyperbolic sine. I guess it doesn't technically have to be, but that's the natural partner. And A2 equals 0. Because hyperbolic sine does not satisfy the boundary condition there. So there can't be any contribution from hyperbolic sine. All the contribution comes from hyperbolic cosine. So 100% of our solution is this hyperbolic cosine as long as we put it as a function of 1 minus x instead of x. Okay, so in the end, we only have to worry about solving A1 now. Okay, so C of x is equal to A1 hyperbolic cosine of phi times quantity 1 minus x. So now use constant flux at x equals 0 to find A1. Okay, so let's take the derivative here, right? So dc dx is equal to minus a1 hyperbolic sine, minus a1 times phi times hyperbolic sine, sorry about that, times phi times hyperbolic sine of phi times 1 minus x. And at x equals 0, this becomes dc dx at 0 equals to minus a1 phi times hyperbolic sine of phi. And therefore, according to our boundary conditions, that has to be constrained to be equal to -1, the constant flux. So that's how we find A1. So A1, finally, A1 equals to 1 over phi times hyperbolic sine of phi, which finally gives us our final answer. Our concentration of x is equal to hyperbolic cosine of phi times 1 minus x over phi times hyperbolic sine of phi. All right, that's ugly. It's actually not. It's actually kind of elegant. I mean, it can be written down very simply in terms of transcendental functions that we are familiar with. Right? We don't have some sort of Bessel function in there. You know, a Bessel function is like a function that's represented by an infinite series of terms. You know, there's not some integral in there that we can't evaluate. So it's pretty straight up. And if you don't like hyperbolic cosine, just accept the fact that these are just a linear combination of exponentials then to you, right? It's the average between e to the x and e to the minus x. That's what hyperbolic cosine is. So, so that's our final answer. Well, it's not totally our final answer, and that's because there's one simplification you can make for it. If phi is large enough, then, oh man, I didn't design this very well because I didn't mean for that text to be split to the next page. I definitely had room up here to like shrink things down. Oh well, that's okay. So if phi is large enough, then what that means is, well, let's illustrate what phi is actually doing here. As I change phi, what does c of x look like? So if I change phi to be very small, if phi is very small, phi small, then c of x looks like this. That's not supposed to curve up at the end. It's supposed to stay flat, right? So you have some sort of negative slope in the beginning, and it flattens out very quickly. That's for phi small. How do we know this? Well, let's scroll up. Let's scroll up to our original differential equation. If we're working with the phi version of the differential equation, phi controls the what? The rate of what? What is this term? This one's diffusion. This one's what? What's that? so phi determines the length scale, correct? Or it's, phi is 1 over the length scale. But this term itself physically means what? The minus k times c. It's the rate of degradation, right? So when you non-dimensionalize the equations, phi takes the place of the degradation rate constant here. So phi is very small. That its scaled degradation rate is very small, which means there's not much degradation, which means it accumulates in the system before it reaches steady state. So it accumulates to high levels in the system before it reaches steady state. So you have and it also has a very long length scale if phi is small, right? So it can diffuse very far, so it's pretty much flattened out in the whole system. And there's a lot of it because it's not being degraded very much. So that's what phi small looks like. Phi medium looks like this. This is phi medium. So there's just enough of it for it to kind of extend all the way through the embryo, right? Where L is over there. And if you have phi large, then you have a lot of degradation in the system. And plus, it's 1 over the length scale, right? So if you have a large phi, then you have a very small length scale, so diffusion doesn't go very far. And there's a lot of degradation, and so it basically drops to 0 very, very quickly. Okay, so that's like kind of a let's think about this analysis. But let's actually use the equation to see if this is right. Okay, so we're going to ignore for now the constant, this A1, and we're just going to look at what is cosh. I promised myself I wouldn't say that. What is the hyperbolic cosine? Cosh. Okay. Hyperbolic cosine of phi times 1 minus x. That's equal to, if I expand it in terms of exponentials, then I have 1/2 times e to the phi of 1 minus x plus e to the negative phi 1 minus x. So if phi is large enough, then this simplifies down to 1/2 e to the negative, to the phi of 1 minus x. Phi times 1 minus x. If phi is large enough, then as long as x isn't like almost exactly equal to 1, this second exponential is very, very, very small. So we can ignore this second term, and we pretty much only keep the first term. Okay, and you can pull out e to the phi, and so this is equal to 1/2 e to the phi times e to the negative x. Negative phi x. It turns out if you look at the hyperbolic sign and split that out and like the hyperbolic sign of phi in the denominator, this ends up canceling out. And I think it's actually phi times the hyperbolic sign of phi. This ends up canceling out to be 1/2 e to the phi. I could be wrong about that. There might be a 1 over phi actually in there. Yeah, forget that first phi there. Okay, so the hyperbolic sign of phi ends up being e to the phi, 1/2 e to the phi. So when you normalize by that, in the end, what this means is that c of x is approximately equal to 1 over phi e to the minus phi x. I think that's right. I might be wrong about this 1 over phi. But the important point here is that if phi is large enough, then the exponential, the hyperbolic cosine, gets close enough to 0 before you hit x equals L, that the whole thing just looks like a regular old exponential decay. E to the minus x is just what it looks like. And so phi large enough being this scenario or larger. It just looks like e to the minus x. If phi is too small, then this boundary starts to interfere with that, and then you kind of start to look flat, right? It doesn't decay to 0. It decays to something that's not 0. But if phi is large enough, which ends up being about 5 or larger, roughly. Maybe 3. 3 might qualify, but kind of in that range. Okay, and this is the classic distribution of the morphogen gradient, e to the minus x, right? Last point, so if phi is so large, and that means that the concentration of Bicoid is decaying to close to 0 pretty quickly, what that does, as far as the Bicoid is concerned, it makes it look like the end of the embryo, the other end, x equals L, is really far away. I guess I should say x equals 1, but it looks like it's really far away to Bicoid, which kind of means that you're also, at least in approximation, you're satisfying this boundary condition. So if we had that boundary condition instead of the no flux boundary condition, then it would be e to the minus x. That would be the right answer. And so as long as phi is large enough, then x equals 1 looks pretty darn far away to Bicoid. And so you kind of approximately satisfy this boundary condition. Okay? The reason why I say this is because some people will simplify their morphogen models this way.